Hello guys, and welcome to my YouTube channel. In this video I am going to explain PCB Gerber file extensions and what each output file means. The top copper layer is one of the most important Gerber files in a PCB manufacturing package. This layer defines the conductive copper pattern on the top side of the board, including traces, pads, vias, and copper pores. Every signal that travels across the top side of the PCB follows the paths created in this layer. When a component pin needs to connect to another component, the copper trace becomes the electrical road between them. Pads provide the soldering area for component leads, while vias allow signals to move from the top layer to other layers inside the board. Copper pores are often used for ground, power, or thermal improvement. A well-designed top copper layer can reduce noise, improve current flow, and make routing more efficient. This is why, before sending a PCB to manufacturing, the top copper Gerber must be carefully checked for correct connections, clearances, trace widths, and pad geometry. The bottom copper layer defines the conductive copper pattern on the underside of the PCB. Even though it is physically on the opposite side of the board, it works together with the top copper layer to complete the circuit routing. In many PCB designs, especially two-layer boards, the bottom copper is used to route signals that cannot easily fit on the top side. It can also contain power traces, ground pores, test points, and via connections. When a trace needs to jump from the top side to the bottom side, a via provides that vertical connection through the PCB. Bottom copper is also useful for creating larger copper areas, which can help with current carrying capability, grounding, and heat spreading. In a good layout, the bottom copper is not just a backup routing layer. It is part of the electrical structure of the board. That is why designers must review it carefully for spacing, shorts, isolated copper islands, and correct connectivity before production. The top silkscreen layer is the printed information layer on the top side of the PCB. Unlike copper layers, it does not carry electrical current, but it plays a very important role during assembly, inspection, testing, and repair. This layer usually contains reference designators such as R1, C3, U2, and J1, which help identify components on the board. It may also include component outlines, polarity marks, pin 1 indicators, logos, revision numbers, warning symbols, and assembly notes. For example, a diode, LED, electrolytic capacitor, or connector must be placed in the correct direction, and the silkscreen helps show that orientation clearly. A clean silkscreen makes the PCB easier to understand, especially when someone else needs to assemble or debug the board. However, silkscreen should not overlap exposed pads or very small component areas, because it can create printing problems. A professional top silkscreen layer improves readability and makes the final board look more organized and reliable. The bottom silkscreen layer provides printed information on the underside of the PCB. This layer is especially useful when components are mounted on both sides of the board, or when technicians need to inspect the board from the bottom side. It can include reference designators, component outlines, polarity marks, connector labels, test point names, board revision details, warning symbols, and manufacturing information. Although the bottom side is sometimes less visible in the final product, it can still be very important during production and troubleshooting. For example, if a test point is placed on the bottom side, a clear label helps the technician quickly identify the correct signal. If a connector or capacitor is mounted underneath, orientation marks can prevent assembly mistakes. Like the top silkscreen, the bottom silkscreen must be clean and well spaced. Text should be large enough to print properly, and markings should not interfere with exposed copper pads. A good bottom silkscreen makes the PCB easier to build, inspect, and maintain. The top paste layer is used for surface mount assembly. It defines where solder paste should be applied on the top side SMD pads before components are placed. This Gerber file is used to create the stencil, which is usually a thin metal sheet with openings cut exactly where paste is needed. During assembly, solder paste is pushed through these stencil openings and deposited onto the pads. Then the surface mount components are placed on top of the paste. After that, the board goes through a reflow oven, where the paste melts and forms the solder joints. The size and shape of paste openings are very important. Too much paste can cause solder bridges, especially on fine-pitch ICs. Too little paste can create weak joints or poor electrical contact. For thermal pads under QFN or power components, paste openings may be divided into smaller windows to reduce voiding. The top paste layer directly affects solder quality, assembly yield, and long-term reliability. The bottom paste layer defines solder paste openings for surface mount components placed on the bottom side of the PCB. This file is required when the board has SMD parts mounted underneath, especially in double-sided assembly. Just like the top paste layer, it is used to manufacture a stencil that controls where solder paste will be deposited. The bottom paste file tells the manufacturer which bottom side pads need paste and how large each paste opening should be. This is important because paste volume must be controlled carefully. If the openings are too large, components may shift during reflow, or solder bridges may form between pads. If the openings are too small, the solder joint may become weak or incomplete. Bottom side assembly also needs extra attention because parts may pass through more than one heating process. Good paste design helps maintain consistent solder joints, strong mechanical connection, and reliable electrical performance. For professional PCB manufacturing, the bottom paste layer must match the bottom side SMD component pads accurately. The top solder mask layer defines the protective coating on the top side of the PCB. This is the colored layer that usually gives the PCB its green, black, blue, red, or white appearance. Its main purpose is to cover and protect the copper areas that should not be exposed. By insulating copper traces and pores, the solder mask helps prevent oxidation, accidental shorts, and solder bridging during assembly. Only selected areas remain open, such as component pads, test points, and some via openings if needed. This is why the solder mask Gerber is very important. It tells the manufacturer where the mask should be removed so copper can be soldered or contacted. A good solder mask design improves board reliability and makes assembly much easier. It also helps define clean spacing between pads, especially on fine pitch components. If the mask openings are wrong, pads may be covered, soldering may fail, or unwanted copper may remain exposed. So this layer is critical for both protection and manufacturability. The bottom solder mask layer protects the copper on the underside of the PCB. It works the same way as the top solder mask, but it applies to the bottom side of the board. This layer covers copper traces, copper pores, and other conductive areas that should remain insulated. It leaves only the required pads, test points, mounting contacts, and selected openings exposed. Without solder mask, copper would be more vulnerable to oxidation, contamination, accidental shorts, and solder spreading during assembly. The bottom solder mask is especially important when the PCB is installed inside an enclosure or close to metal parts, because it helps prevent unintended electrical contact. It also improves the finished appearance of the board and makes it easier to handle safely. In production, the solder mask opening must align correctly with the pads. If the opening is too small, it may cover part of the pad. If it is too large, too much copper may be exposed. Good bottom solder mask design improves durability, insulation, and manufacturing quality. Inner layers are used in multi-layer PCBs and are located inside the board, between the outer top and bottom layers. These layers are not visible after manufacturing, but they are extremely important for electrical performance. Inner layers can be used for signal routing, power distribution, and continuous ground planes. In more advanced designs, one inner layer may be dedicated to ground, while another may be dedicated to power. This helps reduce noise, improve return current paths, and provide more stable voltage delivery to components. Inner signal layers can also help route complex circuits when there is not enough space on the outer layers. For high-speed designs, inner layers are especially valuable because they can support control impedance routing and better electromagnetic performance. The layers stack up, dielectric thickness, copper weight, and plane arrangement all affect the final behavior of the PCB. A well-planned inner layer structure can make the difference between a noisy, unstable board and a reliable professional design. Drill files are not standard image-like Gerber layers, but they're still essential PCB manufacturing outputs. They tell the manufacturer exactly where to drill holes and what diameter each hole should be. These holes include vias, through-hole component holes, mounting holes, tooling holes, and non-plated holes. Vias are used to connect copper from one layer to another, while through-hole component holes allow leads from connectors, headers, and other parts to pass through the board. Mounting holes are used for screws or mechanical attachment. The drill file usually contains coordinates and tool sizes, so the drilling machine knows which drill bit to use for each hole. If the drill file is missing or incorrect, the PCB cannot be manufactured properly, even if all Gerber layers are correct. Hole size is also very important. Too small, and the component lead may not fit. too large and soldering or mechanical strength may suffer. Accurate drill files ensure proper electrical connection, assembly fit, and mechanical reliability. Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.